Now, in the previous lesson, we have looked at uh, some kind of generalizations of multiple points moving average, that kind of an idea. So we started from this kind of a 3-point average, and we did a Matlab script to show that this kind of 3-point moving average is indeed a low-pass filter, right? It's a low-pass filter. And then we generalized that idea, right? Instead of doing just a 3-point average, we're doing a this many point moving average. It's basically big N plus 1, this many points. So K goes from minus big N to positive big M, and we are doing a moving average with a variable with a with a number of points being configurable, right? And then we got the Fourier transform, the transfer function, basically the transfer the Fourier domain transfer function, and it looks like something like that. And we did a comparison using 16 points, right? Big M plus big M, big N equals to big M equals to 16, right? And then we also did a comparison with 32 points, right? 32 points moving average, and we found that the 32 points moving average is actually performing better than the 16 points moving average, right? And then we did one more generalization, right? So for this particular formula, the weights for each of the point is exactly the same. It's 1 divided by big M plus 1. It's equal weight moving average, right? But suppose we can choose the weights. Suppose we can actually make the weights configurable. It also depends upon K, so BK. It's no longer a equal weight moving average. It's a weighted moving average, right? And the weights are given by BK. And BK actually depends upon K, right? And we still considered 16 points. Big N equals to big M equals to 16, right? A 16-point moving average. But the weights BK are chosen to have this particular form. It's basically a sinc function, right? It's a sinc function of K, right? And for K smaller than or equal to 32, it's a sinc function, and then for K larger than 32, it's exactly 0, right? So it's still a 32-point moving average, but with variable weights, right? And then for this particular filter, for this particular low-pass filter, its impulse response looks something like that. And we can actually plot its spectrum if we do a Fourier transform of ht and then make a plot of it. That's basically the red line here, right? The red line here. This is the vertical axis is in dB. The horizontal axis is actually in pi, right? It's in pi, and we found that this variable weight 16-point moving average actually performs better than the equal weight 16-point moving average, right? Which is the blue line here, right? And we did a short script to do this comparison, right? And last time I was just typing all the commands in the command window, but this time I'm actually moving all those commands into a script, right? So for this particular figure, the script for generating that figure was here. Here I'm actually doing the equal weight 16-point moving average, right? And I'm actually plotting the gain of the filter, right, in dB. That's the blue line here. That's the blue line here. And then here I'm actually plotting. So here I actually constructed a sinc function, right? Sinc function based on this formula. That's the impulse response of that filter. And then I did a Fourier transform, right? And then I made a plot of the impulse response in the Fourier domain, also in dB, and that's the red line. That's the red line here, right? That's generated by this particular line, right? And that's the red line, and you can sort of see the passband is flatter. It's more or less flat with some wiggles on it, but it's more or less flat, right? And then the stop band has smaller amplitudes than the equal weight 16-point average, right? So this example actually allows us to shows us that by carefully choosing the weights used for the moving average, we can achieve a better low-pass filter. But now let's look at the weights. Look at the impulse response. Look at the impulse response, right? So Hn is the impulse response of this particular low-pass filter. This variable weight, 16-point moving average low-pass filter. Right? That's the impulse response. And what this impulse response actually shows that it's a sinc function, right? For n smaller than or equal to 32, it's basically a sinc function, right? It's a sinc function. And then for n larger than 32, the amplitude of the impulse response is exactly 0, right? So if we think about the sinc function, we looked at the sinc function before, right? It looks something like that, right? The reason that I called this particular filter infinite impulse response is because this oscillation keeps going on. The amplitude gets smaller and smaller, but it's gonna keep oscillating with non-zero amplitudes, right? Even though the amplitude will become smaller and smaller, right? But nevertheless, it has non-zero amplitudes at infinity. So it's a infinite impulse response. Right? That's the raw sinc function. The sinc function um, do not have a compact support, right? But for this variable weight moving average, its impulse response is still a sinc function, right? But it's a sinc function only within a limited range of n. So n only appears, it's a sinc function only for n, the absolute value of n smaller than or equal to 32. And for n is larger than 32, its amplitude is exactly 0. So if I want to make a plot, of time domain h, suppose I generate another figure, and then do a stem, and h, right? And then I'll just do an xlim, say minus 50 to positive 50, right? That's sort of the time domain impulse response of that low-pass filter, right? In the center part, within the 32 range, minus 32 to positive 32 range, it's still a sinc function. But outside of this range, it's exactly 0. So we obtained this low-pass filter effectively by zeroing out some part of the sinc function where its amplitude is small. Right? We kept only the center part of that particular sinc function, and zeroed out the rest of the sinc function. Right? So and that actually gave us a quite good low-pass filter, right? So what we have done? What we have done is basically we have converted this infinite impulse response low-pass filter into actually a finite impulse response filter, right? By just zeroing out some part of the sinc function. We know that this sinc function actually corresponding to a boxcar, a square wave in the Fourier domain. And for this modified sinc function, we know its Fourier domain representation, its Fourier domain amplitude, it still resembles a boxcar, but with ripples both in the pass band and also in the stop band. And the consequence of zeroing out those small amplitudes of the sinc function in the time domain is basically now you have those ripples, right? So maybe we can actually generalize this idea. And try to sort of come up with a systematic way for constructing what we call the finite impulse response filters. The reason it's called finite is because it's non-zero only on a finite interval. It has compact support. The impulse response has compact support in the time domain, right? So let's try to investigate a systematic way for us to construct FIR, right? By just generalizing this idea, right? By generalizing this idea. But before we do that, we need to consider two things. One is what we call the linear phase filter. Right? Linear phase is actually something that's quite desirable. We would like our filter to have linear phase or zero phase actually. But linear phase is actually the second best thing. If it has a zero phase, then it's probably better. But if it has linear phase, it's still acceptable. It's not too bad, right? But if it has a non-linear phase, it has actually a very complicated phase for the filter, then it's not something that we would want, right? Because those phases in the filter is going to change the waveform. It's going to change the waveform of the input signal. It's going to distort the waveform, right? And it makes the input signal look very different from before filtering. So linear phase filter is like a quite a desirable feature for any kind of filter. So let's try to understand what linear phase filters are. So when we talked about the various properties of the Fourier transform, we sort of emphasized this kind of time shifting property, right? So the Fourier transform of a shifted signal here, xn is the signal, is the original signal, but xn subtract k is the original signal xn shifted by k units to the right, right? So the Fourier transform of the shifted signal equals to the Fourier transform, big X is the Fourier transform of the original signal xn multiplied with e to the minus j omega k, and k is exactly the shift, the amount of the shift, right? So if we look carefully about this particular complex exponential that's being multiplied to the Fourier transform of the original signal, it's actually a linear phase, right? It has a linear phase. The reason that it's called linear phase is because it's k, right? It's a linear function of omega, right? So if you actually multiply the Fourier transform of small x, that's big X, with a linear phase stuff in the Fourier domain, right? The effect in the time domain is basically just the shifting the time domain signal by a certain amount. So it's not going to change the shape of the input signal. It's just going to shift it, right? It's going to just shift it by a certain amount in the time domain. It's not going to change the shape of the input signal, right? And this is actually a consequence of the time shifting property of the Fourier transform, right? So if we consider a filter that has a transfer function big H as a function of omega, right? And then if we can actually write this filter as its absolute value times e to the minus j omega k, some linear function, right? Then this big H, this transfer function, is called a linear phase filter. And of course, it's going to change the amplitudes. It's going to change the amplitudes, the amplitude spectrum, right? But its phase is linear. So the consequence of the phase is just to shift the time domain signal by a certain amount, right? And of course, if we replace e to the j omega with a complex number that's called a z, then we can actually write this particular linear phase filter in a more compact form. Hz equals to the absolute value of Hz times z to the minus k. See, it's linear, right? So linear phase filter is something that's desirable. Let's look at one example, right? Let's look at one example. Suppose our filter has a transfer function that looks like that, right? That's expressing it using z. But if you are not familiar with this kind of z representation, you can still switch back to the e to the j omega using the frequency domain representation, right? Then it means what? It means this filter has a constant amplitude, alpha. Alpha is a constant. It doesn't depend upon omega. It's a constant. And then e to the j omega times minus big N 0, right? And then minus big N 0, this is a constant. It doesn't depend upon omega. So the phase is still a linear function of omega, right? The phase is still a linear function of omega. And then suppose the input signal is xn that looks like that. Looks something like that, right? And then we apply this particular filter onto this particular input signal. Then what's going to happen, right? What's going to happen? So effectively, we have to sort of suppose we convert xn into Fourier domain, and we get big X omega, right? And then we have to multiply big X omega with big H omega. That's the transfer function. That's the transfer function of the filter, right? And then what we get is big X omega multiplied with alpha e to the j omega minus big N 0, right? And we know that alpha is a constant, right? And this is actually a linear phase, right? So multiplying this complex exponential in the Fourier domain is essentially equivalent to translating or shifting this input signal by a certain amount in the time domain. And that amount is minus N0, right? So the output signal for this particular input signal is going to become what? It's going to become, first of all, you have to change the amplitude, right? You have to change the amplitude. The input signal is actually composed of three separate signals, right? One cosine omega 0 n plus cosine 2 omega 0 n. Right? The amplitude effect is to multiply with a constant alpha. So you have to multiply alpha on each of the terms. So you get alpha multiply 1, that's alpha, right? And then alpha multiply this cosine, you get alpha cosine, right? And then alpha multiply this cosine, you get another alpha cosine, right? That's the effect of the amplitude. Then what's going to be the effect of the phase? It's a linear phase, right? So multiplying a linear phase, a complex exponential with a linear phase in the Fourier domain is equivalent to shifting the input signal in time domain, right? And the amount of shift is minus N0, right? So effectively, the output signal is going to be alpha multiplied with 1 plus cosine omega 0, shifted by alpha, shifted by big N0, minus big N0, then you get N subtract big N0, right? Plus cosine 2 omega 0, shift again, you get N subtract big N0, right? So basically, the shape of the output signal is pretty much the same as the input signal, except that it has been shifted. The entire signal has been shifted by minus big N0, and it has been scaled by a constant alpha, right? So that's basically the effect of a linear phase filter. It's not going to change the shape of the input signal. It's just going to shift the input signal by a certain amount, right? But alpha might be something that you can control, right? Maybe you can make it into a boxcar or something, right? And then you can sort of choose the frequency content you want, right? So that's something that we call a linear phase filter, right? A linear phase filter is something that's desirable. We want a linear phase filter. And then the frequency scales, right? So far we have introduced several different types of representations for frequency, right? The one that you are probably most familiar with is probably hertz, right? That's the inverse of seconds, right? Inverse of second. So you can represent frequency in hertz, right? But for the horizontal axis, usually the frequency axis is from minus infinity to positive infinity. But usually people only plot an interval that goes from like 0 to half of the Nyquist frequency fs. Right? The reason that people are plotting it is because plotting only just this particular interval is because, first of all, it's the discrete Fourier transform is actually cyclic. It has a fundamental period of 2 pi within the on the frequency axis, right, in the frequency domain. Right? A second thing is that it has this kind of symmetry across 0, right? That's one of the Fourier transform properties. If your time domain signal is actually real, then the negative frequency is actually the conjugate of the positive frequency content. Right, so there's redundant information in the negative frequency part. Right, so usually people can forget about plotting the negative frequency part, just plotting the positive frequency part. Right, that's in terms of hertz. Right, but if you want to use angular frequency, you can multiply a 2 pi on hertz. So this is Nyquist frequency in hertz, and then if you multiply 2 pi, you get big omega s. That's the Nyquist frequency in terms of radian, the angular frequency. Right, and of course you can also normalize it into pi. So you can actually look at the frequency range goes from like minus pi to positive pi. That was the frequency range that we have sort of used before, right? And then you have another kind of normalization which goes from like 0 to 1, right? You basically divide this small omega by pi, right? And for any of these kind of choices, all those choices are actually equivalent. It just differs by a scaling factor, right? And for each of those choices, you have the corresponding pass band, stopping band, right? For each of them, you have fs, fst, big omega p, big omega st, stop, right? That's pass, that's stop, pass, stop, pass, stop, right? So you can design your filter using any of those axes. It doesn't really matter too much, right? It's just differs by a scaling factor. It depends upon your own convention, right? It depends upon your own habit. But if you choose one frequency scale, it's better to stick with it, right? And to make sure that everything is consistent. So that's frequency scales, right? And different kinds of frequency scales, right? So now let's try to think about finite impulse response filter design through windowing. Windowing means what? Through windowing the impulse response of a infinite impulse response in the time domain, right? Just like the idea that we have discussed before, right? We actually obtained this particular impulse response for low pass filter by just zeroing out a sinc function, right? But let's try to sort of think about this kind of thing in a more systematic way. So we have a certain target transfer function. That's the transfer function that we would like to get, right? Let's call it big HD as a function of omega. That's the target. That's the desired transfer function for a certain filter. Let's assume that the phase is exactly 0 for this particular desired transfer function. Which means what? Which means that in the frequency domain, this HD is basically a real function. It has only real part, right? Because the phase is 0, right? So it should be symmetric. A real function symmetric with respect to omega equals 0, frequency equals 0, right? And for this desired transfer function, right, we can get its time domain impulse response by just doing an inverse Fourier transform, right? That's our inverse Fourier transform formula. We have chosen the integration range to go from minus pi to positive pi. It doesn't have to be, right? But using minus pi to positive pi is like the convention, right? It doesn't have to be. It can be any 2 pi interval, but minus pi to positive pi is a widely used convention, right? That's basically the inverse Fourier transform. And if you have this time domain representation, that's the desired impulse response in time domain. Let's call it small HD. Once you have it, you can also get back HD by doing a forward discrete Fourier transform, right? That's the forward discrete Fourier transform formula. So once we have decided on a big HD in the Fourier domain, we can compute a small HD in the time domain, right? And we can also get back the big HD by doing a Fourier transform of the small HD, right? That's the desired target transfer function. So now we have to come up with the windowed impulse response in the time domain, right? So small HD is sort of the inverse Fourier transform of big HD, right? But now we multiply with a time window, with some kind of time window. And the result, this is the time domain multiplication, right? The result we denote it as small hw n. This small hw n has this kind of property. It equals to small hd within this particular range. So big N is some number that you can choose, right? And then 0 everywhere else. So it's basically just like this kind of thing, right? You are selecting a certain part of HD and then zeroing out everything else, right? And this Wn is just a time domain boxcar, right? It equals to 1 within this range and then 0 everywhere else, right? So that's the time domain windowing operation. And after this windowing operation, we get a new function, new time domain function, HW, which is basically the windowed HD, right? Then, what's the effect of windowing, right? So let's bring this HW, small HW, back into Fourier domain by just doing a Fourier transform, right? So this is basically a Fourier transform because HW, small hw is non-zero only within this range. So your summation index can go from like a minus big N subtract 1 divided by 2 to big N subtract 1 divided by 2, right? So you can limit the range of the summation because it's non-zero only within this range, right? But if N is large enough, if we make big N very large, extremely large, then we have big HW should be approximated to big HD, right? It's a good approximation. Big HW should be a good approximation of HD. So now you have established some kind of approximation of your desired filter, right? And you can make the approximation arbitrarily good by making big N large enough. You see? So if big N is very large, it means that the window is very wide, right? If you multiply with a very wide window, then HD and HW, small HD and small HW, becomes very close to each other, right? If you actually make big N infinity, then HD is exactly equal to HW, right? So as you make big N larger, small HD becomes closer to small HW. And in the Fourier domain, you also have the same kind of relation. Big HW becomes closer and closer to big HW as you increase big N, right? So now we want a causal filter. Last time I was telling you guys if the filter actually if the impulse response of the filter actually has non-zero amplitude in the negative time, then it's non-causal, right? And a non-causal filter cannot be implemented, for example, in real time. You need to know the future values of the input signal in order to actually compute the filtered signal, right? So it's impossible to implement it in real time, right? So usually you would prefer to have a causal filter. So what we're gonna do, we're gonna shift HW, this windowed time domain impulse response, by these many points, right? Because small hw is actually symmetric, right? It's non-zero from this number to this number, right? The window is actually symmetric. So what you can do is if you actually shift it by this many points to the right, then you have 0 amplitudes on the negative time axis, right? So by doing this shift, you are making a causal filter, right? And what's going to be the effect in the frequency domain for this particular shift, right? You're basically multiplying big HW with this particular linear phase, right? And that's the amount of the shift, right? That's the amount of the shift minus big N subtract 1 divided by 2, right? And of course, we can represent the big HW, can represent this big HW by using its Fourier domain representation. That's using its time domain representation, HW, right? So from this step to this step, basically we are just doing a Fourier transform, right? So big HW equals to the Fourier transform of small HW, right? E to the minus j omega m. Here I'm actually using the index m, right? Index m, right? And then we can combine the phase together. And now all we have to do is to do a change of variable, right? We just replace this m plus big N subtract 1 divided by 2 with another variable that's called n, right? So here it becomes e to the minus j omega n, right? And HWM has to be replaced with n subtract big N subtract 1 divided by 2, right? And also the range of the summation can now be changed back to for n actually goes from 0 to big N subtract 1, right? So shifting actually makes our FIR filter caudal, and this effect of the the effect of the shifting in the time domain in the frequency domain is just to multiply a linear phase, right? Complex exponential, right? So now let's look at our filter. Let's look at our filter. Our filter actually is denoted as big H hat at function omega, right? If we look at big H hat as a function of omega, it equals to what? It equals to big HW multiply with this linear phase, right? And if we actually take the absolute value, right, the amplitude of the filter, it equals to the amplitude of big HW, right? And if we take the phase angle equals to what? It's a linear phase, right? It's just being shifted, right? So it's a linear phase filter, right? And the amount of shift is minus big N subtract 1 divided by 2, right? So now let's look at how we can actually implement this kind of calculation in Matlab, right? Let's look at how we can actually implement all those design process design steps in Matlab, right? So now let's try to go through all the different steps in the FIR filter design by windowing, right? And the first thing we're gonna do is to pick a target filter, right? Suppose we still pick the uh, the the ideal filter. That's the square wave, the boxcar. This kind of a filter as our target filter, right? The target. But this filter in time, this is in frequency domain, and in time domain, it's a sinc function. The impulse response of that boxcar is actually a sinc function. So our that's gonna be our target, right? So HD, big HD, our target is gonna be that boxcar, right? And then small HD, the time domain representation of that target filter is gonna be the sinc function, right? We have picked our target, right? And then the next step is windowing. We have to sort of window that target, the impulse response of that target filter by using a time domain window, W, right? Here we're actually assuming the time domain window is a boxcar, right? If we actually use this kind of boxcar, we end up with something that's kind of similar to that 16-point average variable weight 16-point averaging study example that we did. Um, so the window is actually the time domain window that you multiply on this desired impulse response is actually quite important, right? And it's gonna give you different behavior for the final filter, right? So we need to study. What's actually the effect of different kinds of filters, different kinds of time domain windows, right? And in Matlab, we have several choices for time domain windows, right? So let's look at just a few of them. We're gonna look at 4 of those windows provided by Matlab. So big L is gonna be 64. That's the number of points that we're gonna use to represent that time domain window. And then the first window we're gonna look at is generated by a function called Kaiser, K-E-I-S-E-R. This particular function takes two input variables. Big L is the length of the output window, and then there's a parameter called beta. This beta is gonna control the tapering of that particular time window, right? So it's not the time window. The time window is not going to be a boxcar, but it's going to be tapered on the sides of the two sides of the window. And how smooth that tapering is controlled by beta. So the first input is going to be big L, and then the second input, let's give 0. So we assign beta with a value of 0. So no tapering. So in this case, it's supposed to give you a boxcar basically. And then W2, the second type of window that we're going to look at, is called Bartlett. B-R-T-L-E-T-T. And then it takes just the one input. And then that's the length of the window. And then on the third window we're going to look at is called Hamming. And then it also takes just the one input. Then W4. For W4 we're going to look at Kaiser again, but with a different beta value. Let's use 20. Right. So for 1, 2, 3, that's 3 functions, right? 3 functions for generating windows. If you are not, if you haven't used those functions before in your coding experience, you can just do a help, right? Help Kaiser. Then it's gonna display how to use this particular function. Returns the endpoint Kaiser window in the column vector W, right? So, and then you also have help Bartlett. That's for generating a Bartlett window. And then Hamming. Right? That's for generating a Hamming window. Right? There's also another window function that's called Henning. Right? It's a Henning window or Hamming window. Right? It's very close to each other, but they are actually different. Right? It's actually different. And then let's try to look at those windows. And Matlab actually provides a very nice visualization tool for us to examine different kinds of windows. It's called the WV tools. And then all you have to do is to put those windows that we just generated as input to WV tools. 4. Right. And if you haven't used WV tools before, you can type help WV tools, and it's gonna WV tool, I think WV tool, not tools. And then it's gonna window visualization tool, right? It's a graphic user interface that allows you to examine and analyze windows. Right? So let's execute this block. WV tool, sorry. Right. And then it's gonna give you this kind of output. Right. So on the left side, it's the time domain window for the 4 different windows that we have typed. Right? Kaiser L0, Bartlett, Hamming, Kaiser L20, the 4 different windows. So you can sort of see 4 curves here. And then on the right side, it's the frequency domain representation of those windows. It's basically the amplitude. It's the horizontal axis is in terms of frequency, normalized frequency, basically. Right? The vertical axis is in dB. It's basically the amplitude of the Fourier transform of each of those windows. And the color code is the same for the left and the right. Right? If you want to see the color legend, you can click on this button. It's gonna give you the color legend. Right? Let's just move the color legend somewhere that's less interfering. Maybe let's move it here or something. All right. So you can sort of see. So window 1 is blue line, right? That's Kaiser L0. So no tapering. That's a boxcar, right? And its corresponding Fourier transform, the amplitude spectrum of the Fourier transform of the boxcar, looks like that, right? it's supposed to be some kind of sinc function, but you are looking at just the positive frequency part of it. Negative frequency is supposed to be symmetric, right? And then Bartlett is that's the second window. That's um, this green line, and the green line is the thing that looks like a triangle here, right? And in the Fourier domain, that's the green curve, right? And you can sort of see this green curve actually looks better than the blue curve, right? The the high frequency content is further attenuated, right? And then you have Hamming window. That's the third window. That's the red curve, right? It's a very smooth curve, right? It's a very smooth curve, Hamming window. And in the frequency domain, that's the red line. So the Hamming window, at least for the second and third lobe, it looks better than the green curve, right? The Hamming window. And then the last one is Kaiser L20. So if you compare Kaiser L20 with Kaiser L0, huge difference, right? That's the Sion curve, I think. This Sion curve is much smoother than this boxcar, right? And in the Fourier domain, you can sort of see it's a very good low pass filter actually. Sorry, it's actually a very good low pass filter. So that's the different kinds of windows that can be used for us to actually window the impulse response of our desired uh, filter, right? So let's just close it. Let's close it. That's lots of it. We have lots of choices we can pick from, right? But what's actually the effect of those different choices, right? What's actually the effect on the final filter, right? Once we actually have picked a specific window, right? So now let's look at the effect of those different filters, right? So let's first construct HD, right? Our desired filter is sort of a boxcar in frequency domain, then it's supposed to be a sinc function in the time domain, right? So let's try to construct a horizontal axis. N goes from -10 to +10, suppose, right? Suppose some arbitrary range, and then our desired filter H here is the HD basically, right? It's supposed to be a sinc function, so sine pi times n divided by 4, suppose, right? Dot divide pi times n. Right, that's our H, right? That's our H. But for this particular H, it's gonna have not a number at n equals to 0, right? Because you're dividing a 0. So for that point, we need to assign a specific value for it. It's 0.25 basically, right? And that point is the 11th point because 0 n equals to 0 is actually the 11th point for the n vector, right? So that's gonna be our the impulse response of our desired filter, right? Even though the range is kind of fixed from -10 to 10, it's just a one segment of it, right? It's just a one segment of the desired the complete sinc function, but we'll work on that because the reason that we're just choosing this particular small range is because the windows that we're gonna apply has a width that's kind of controlled by this range. We're going to use a window that so everything that's outside of this range will be removed by the windowing anyway. So there's no reason for us to actually construct a horizontal range that goes from like 1000 -1000 to +1000. It's unnecessary, right? So if we want to sort of look at what this function actually if we want to look at this particular function, we can make a plot of it. Let's just do a stem nh. Right. Let's So that's a portion of the sinc function, a certain portion of the sinc function from -10 to +10. Right. So suppose we window it using a boxcar like this kind of thing. Wn is either equal to 1 or 0. Then this h function is already, and n, big N goes from like a big N equals to 11, right? 11, big N equals to 11. Then the horizontal range for that window is exactly from 20, 21, 21. Big N equals to 21. So 21 subtract 1, that's 20 divided by 2. That's -10, right? -10. So small n goes from -10 to +10 when big N equals 21, right? So this particular sinc function, actually corresponding to the desired impulse response of the filter, which is infinitely long, multiply with this boxcar time window, right? That's corresponding to Kaiser big L0, right? That's W1 basically, right? So in this case, small h is already small hw if we pick our window like that, right? And then the next step is what? The next step is actually shifting. So because we want a causal filter, right? So what we have to do is to basically just to make a causal filter. All we have to do is to shift h by big N subtract 1 divided by 2. That's basically 10 points, right? In order to shift it, all we have to do is to actually just change the range of n. So we give it a new horizontal axis that goes from 0 to like 20, right? If we hold on to the old plot and then stem n1 edge, right? That's gonna be in red, right? So the red impulse response is sort of the shifted, windowed impulse response, right? That's the third step actually, because we are actually using a boxcar as the window, right? And then the next step is to look at the frequency content. The spectrum, especially the amplitude spectrum of this constructed filter, of this particularly constructed impulse response, basically, right? So how are we going to do that? There's a Matlab function that allows us to visualize the corresponding Fourier domain spectrum of this impulse response, right? And that particular function is called FREQZ, FREQ-Z. And you call that function by doing this big W, that's going to be the output, FREQZ. That's the function name. And then FREQZ takes 3 inputs. If you haven't used FREQZ, what you can do is to just type help FREQZ. Then it's going to tell you how to use it. So it takes 3 inputs, B, A, and big N. It tells you that it's going to compute the frequency response of digital filter, right? And then big H is going to be something like that. And then big W is actually the horizontal axis in the frequency domain for big H. It takes 2 inputs, big B and big A. So big B is basically a vector that corresponding to B1, B2, Bm plus 1. That's the coefficients in the numerator. And then big A corresponding to A1, A2, this vector. That's basically the coefficients on the denominator. Right. And for our particular example, for this particular example that we are going to do, the impulse response that we just constructed, this small h function, this small h function, it's a vector, right? It's actually a vector. This vector actually corresponding to B1, B2, Bm plus 1. This vector. I'll explain why in a future video, right? But for now, let's just use h as the first input, and then for the second input, that's sort of a vector of a. You have a1, a2, an. But in our case, those a2, a3, an plus 1 are all zeros because we are not really dividing anything, right? So the denominator is basically just a 1. So in our case, the a vector is just a single number. That's 1. Again, I'll explain why in a future video, right? And then let's just use h as the first input and 1 as the second input, right? And then it's going to ask you for the total number of points that you would like to use to represent or to sample this big H function, right? Let's suppose we want to use 256. Usually don't really need that many samples, but it's going to be smoother if you use more samples, right? So that's going to be the frequency domain representation of that filter that we just constructed. And its time domain impulse response is given by this small h. Right? If we want to convert between time and frequency domain representations of a specific filter which has the impulse response has a given impulse response, then you can use FREQZ and try to convert it into frequency domain and visualize it. Right. So now let's try to make a plot of it. Make a plot of this big H function. We're gonna generate a new figure and then do subplots. Let's do subplots and then let's do stem n1h that's gonna be our time domain impulse response, right? Time domain impulse response. Big W. Let's normalize it. Normalize it by pi. Normalize the frequency domain by pi, and then we're gonna plot the absolute value of big H. Right. This is plotting the absolute value on a linear scale, right? Suppose we want to plot it on a log scale in terms of dB. In terms of dB, then we can just do 20 times log 10 ABS big H. Right. So the last subplot, we're gonna use it for plotting the phase. Still normalize the frequency, and then we're gonna do a unwrap angle of big H. Right. So the angle of big H is gonna have cycle skips, right? Because the angle could have a cycle of integer times 2 pi, integer number times 2 pi, right? If you do an unwrap, then it's gonna unwrap the phase for you, right? So let's try to execute this block of the code. Right. So that's the time domain impulse response. First of all, it's a finite impulse response, right? It's a FIR, right? Because the duration is finite, and it's actually a linear phase filter, right? Because it's a linear phase causal filter, right? Because the entire sinc function has been shifted. The negative time part is actually zero, has zero amplitudes, right? So it's a causal filter, and it has been shifted by a factor of 10. So you have a linear phase for it, right? And then if you do a Fourier transform of this particular impulse response, the amplitude spectrum of that Fourier transform is going to look like that. And this is plotted on the linear scale. Right? So the horizontal axis is normalized frequency, goes from like 0 to 1 because you divide it by pi. Right? And then the vertical axis is linear. you have ripples on the passband, you have ripples on the stop band, and then you have a transition, right, from passband to stop band. And if you plot it on a log scale, then horizontal axis is still a normalized frequency, but the vertical axis becomes a dB. It's a log scale. Then it's gonna look like that. You have a pretty flat passband, right? And then the stop band amplitude is a lot smaller, right? And this is actually indeed telling you that it's a linear phase in the passband, right? And that's the effect of using the first window, called the big L0, right? The first kind of window, the first window, W1. So now let's try a different kind of window, right? So we tried a boxcar, but now let's try a smoothed window, a tapered window, right? And the window that we're gonna try is Kaiser. How many points do we want? Um, Depends upon the length of H, right? H has 21 points, so we're gonna use 21. And then let's make it smooth. Let's make it smooth by using a bigger beta value. Let's just use 5. The output of the Kaiser function is going to be like a row vector, right? But we might want to use a column vector, I think. We might want to use a row vector. So because H is a row vector, right? And then let's call the output HW. So this time HW is a windowed impulse response, right? And the impulse response is still the sinc function that we constructed here, right? And then multiplied with this smoothed Kaiser window, right? So let's try to sort of again convert it into frequency domain, right? Again, we use a big H W, and then big W equals to FREQZ. Well, you don't really have to use the FREQZ if you don't feel comfortable about using it. Another way you can do it is just doing FFT on the HW, and then plot the amplitude spectrum of the Fourier transform of HW. Right, but here let's just use FREQZ because it's easier. Right, 256. Right, um, and then we can generate another figure, right? And then we can pretty much do everything that we have just done here, right? And then let's just copy it over, paste. So N1H instead of H, N1HW, right? Because that's the sort of the windowed Fourier transform. Right? Do we really want to use a new window, right? So a new figure. Maybe we don't use a new figure, but we're gonna hold on to the old plot, and then we're gonna use a different color, right? Maybe use red. Hold on. Maybe SHW, but use red, right? And then again, hold on. Plot using red. Hold on. Oh, use red. Right. So now let's do a comparison between these two kinds of filters, right? Let's execute this block. Right. So oh, for some reason these two. Oh, sorry. It's not big H. It's HW actually. It's HW, not a big H. So I probably need to remake this figure. Let me. Then execute the second block. So now you sort of see the comparison. The comparison for boxcar window, it's the blue sticks. And then for the smooth Kaiser window, it's the red sticks. Both of them are in time domain, right? That's the time domain impulse response. And then in frequency domain, if you convert them into frequency domain, the amplitude spectrum for these two different filters looks like that. See? So for the filter that's windowed by the Kaiser, the smooth Kaiser window, the red sticks, the amplitude spectrum looks like that. You see, so the ripple for the passband for the red curve is actually smaller. There's less amount of oscillation, right? The same is true for the stop band. Less amount of oscillation here. Ripples are smaller, right? But the transition band for the red curve is larger, right? The transition band for the red curve, and then transition band is for the blue curve, right? So for the blue curve, the transition is actually sharper. It goes from the pass band to the stop band in a smaller amount of distance. But for the red curve, the transition band is wider. It goes from the pass band to the stop band in a longer frequency distance, in a longer range of frequencies, right? It's a smoother transition. That's often the case, actually. If you actually look at lots of different filters, that's often the case. If you want a less number of ripples, less amount of ripples, you usually have to make the transition band wider in order to reduce the number of ripples, right? And then that's sort of the plotting the amplitude spectrum in terms of dB. That's a log scale, right? And you can sort of see this. The red filter is actually better, right? It's actually better in terms of suppressing the high frequency content, right? It's a low pass filter. It passes the low frequency band and then suppresses the high frequency band a lot better than the blue curve, right? The blue filter. And again, the phase is still linear for the pass band, right? So by using a smoother window, by using a smoother time domain window, you actually get a filter that might have some more desirable features. For example, suppressing more high frequency content, right? So that's by using a Kaiser window, right? Of course, you can also look at another kind of window. That's called. Let's try another one. Let's try another one. I'll just modify this code. Instead of a Kaiser, I'm going to use a Hamming. I'm going to use a Hamming window. 21. Right. And this time I'm going to use a different color. Say, let's use black. 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 Right. Again, some slight difference if you actually plot them in the linear scale, but in the log scale, the difference is much more obvious, right? The Hamming window is something that's kind of between the red curve and the blue curve. That's the black curve here, right? That's the black curve here. And because the shape of the window is slightly different, basically, right? So you have some slight differences in terms of the amplitude spectrum and also in terms of the phase. Right. So by using different kinds of window to window your by using different kinds of window, you can actually achieve different effects of your final FIR filter, right? And the effect of the windowing can be predicted. You can actually try different windows and then calculate its frequency domain spectrum, right? Amplitude spectrum, and then compare different kinds of spectrums, different filters, and pick the one that's sort of most suitable for your needs.